Cunningham. I work for Alien Computing. I'm 24. I'm a developer at Alien Computing. That I've read, just sort of diving into AI, and we'll be going through translating some PL1 code to Kotlin using Transformer. So here's a proxy hand code in case we need questions. And I'll start by doing a quick introduction where I'll talk about some basic concepts of sequence-to-sequence models and the transformer models. Then I'll walk you through my entire project. I'll demo what I would have just explained to you in this presentation, and then we'll get to any questions. All right, so to start off, what are sequence-to-sequence models? A sequence-to-sequence model is a machine learning architecture that is designed for tasks involving sequential data. So essentially, this is how a sequence-to-sequence model works. So you have an input and input sequence, which is given to an encoder. This encoder processes it and generates a contextual representation of our data. It's then passed to a decoder who uses this contextual data to generate our output sequence. Now, today we're going to be actually using the transformer architecture, which is a specific sequence-to-sequence architecture. It's a subset. And the core ideas are the same. We've still got our input sequence going into our encoder, passed to a decoder, and our output. There are quite a few extra things going on, but the main one that really set transformers apart when it was introduced by Google already 7 years ago in 2017 is the self-attention mechanism, which is that the transformer can process each word in a sequence, and each word can understand its relationship to every other word in that sequence, no matter how far apart they are, as opposed to just a simple sequence-to-sequence model that every word only gets processed one by one. So we start straight away getting into our project. So we start with setting up our environment with just 3 simple libraries. So PyTorch, which is a really useful library for building and using neural networks. TorchText, which is simply to handle our data. And Antler4, which is used primarily for parsing our PL1 code. We then get to a very important part to be able to train a model, which is the data preparation and the tokenization. So we start by tokenizing our input data. So this is what tokenizing would look like in AI machine learning world, which is we take our sentence or sequence here, we put it through our tokenizer, so we tokenize it, and we get our output tokens here, which are distinct tokens. Is an example of PL1 and Kotlin tokens after being tokenized. Then we would need to define our data set. So this is what a data set generally looks like, which is 80% of the data set is split into a training set, which is used like it's called to train our model. And then the last 20% is a test set, which is used to evaluate our model's performance. Finally, we need to build a vocabulary. So building a vocabulary means identifying each distinct token and assigning it a unique index. So again, here's an example in the PL1 and Kotlin vocabularies that can be created. We then get to 2 functions I had to define. in my project. So first of all, a translation function, where we start by having our input sequence, which is then converted the tokens from this input sequence to their indices. We then convert these indices to a tensor to comply with our PyTorch library for the neural network. We then can start our output. We start the model's prediction loop, meaning we feed our input sequence and the current state of our output sequence. And we loop around each time generating the predicted next token, and we append it to our output until we get an EOS token, so an end of sequence token, and then our loop breaks. We then now convert the indices of our output back to tokens, and we can have our final translation. I then defined a transpilation function where we extract the input tokens and their context, so the input tokens now being Kotlin tokens. We iterate over these tokens to adjust the nesting and the indentation. We then join all these tokens into a single string, and we can return our transpiled code, so formatted correctly now. Finally, just before getting to actually training our model, there are a few parameters that I thought would be important to define and explain to you. So you start with epochs. So one epoch is a complete pass through our entire data set. So the model passes through one time completely the data set. So you can imagine reading a book once. You might not remember the book 2 or 3 times, already a bit more, and 50 times you would have learned a lot about the book. Then our learning rate, which controls how much our parameters are adapted after each step. So a higher learning rate means we change the adapters much more, so which makes the training much quicker, and a lower one, which will make it slower, but will probably make it more precise and give us an optimal solution for our model. And finally, we have the batch size, which is the amount of data our model processes before updating its parameters. And we get to our final setup before our training, where there's another few key elements I thought I'd define and explain. So first of all, the loss function, the model's loss function, is how wrong our model was, how wrong the model's predictions are. The gradients, which are used to show us by how much and in which direction, so increase or decrease, we need to change the model's parameters to reduce our loss function. And the optimizer, which applies the changes that were given to us by the gradients to the parameters and then feeds these new parameters to our model. So we finally get to our training loop. So generally, this is what a training loop looks like when training a model. So you have your training data, which is given as input to our model. Then our model uses its current state of its parameters and generates an initial output, some initial predictions. We then can use these predictions to get a loss. We then use our gradients to see how we can change our parameters to reduce this loss and hence improve our model's accuracy. And finally, we use our optimizer to actually adapt these parameters, and then we keep looping round until the number of epochs, so the number of times we want to loop around, are completed. And finally, here's an example of some training results we could get. So you can have our training losses over there, which are quite high to start, and then after already about 50 iterations or epochs, we're already at quite a precise model. And finally, in my project, I wanted to actually run the model to see whether it actually did the task we wanted it to do. So here, we first read some sample PL1 code. We then set up a Langdev parser to process our PL1 code into a syntax tree. We use a visitor statement to visit each node in our syntax tree and collect the code statements. And we use up my translate and transpile functions to translate the PL1 code into Kotlin and then the transpile function to format it correctly. Yeah.
What does exactly happen to generate dataset? What do you generate? I didn't get that.
We go and get the code statements from the syntax tree that we created using the Langdev parser.
You start with code, right? You start with PLI code.
Yeah.
So what do you build ASD and get back the code?
So we build the ASD and then we fetch the code so that the translation can understand the syntax and the grammar of to be able to translate it.
Right, it's just a chunk that translated also all ASD somehow, right? Or not?
Not really, I don't think.
Do you have an example of what's the input?
So I'm gonna do a demo after, like literally just so we can. Yeah, so in like 2 slides, and I'm gonna actually show the whole project, and we can see a concrete example. So here are just the results of what we'd expect to come from all this. So we'd have our input PL1 code here, and then we would want our output Kotlin code like this. So yeah, now I'd get to a demo, and maybe this answers a bit of your question. So I actually made this whole project in a Jupyter notebook. So Jupyter notebook, I don't know if everyone knows what it is, but it's an interactive web-based interface where you can write prose in Markdown and write and execute your code all in the same place. So yeah, so you can just simply execute it by doing Shift-Enter, and you execute this block of code here, and you get the output immediately. So here I'm just installing the needed libraries, like I explained. Go. So then I'm just importing a few things I need. Execute that. And here I'm defining the custom transformer class. Just execute that to register it. Then we get to actually tokenizing my data. So here we're simply tokenizing it based off of white space. We can then have a quick look again at an example of the tokens we get. Then I'll define my splits. So you can see we've got a training and the test split here. That are 2 JSON files I have. We find the vocabulary. Can have a look again at the PL1 vocabulary here and our Kotlin vocabulary. Finally get to the 2 functions, so the translate function here and the transpile to format it. A few specific functions here, simply to remove the EOS, or end of sequence, from the end of our translation, and simply saving the state of our model after training and reloading it later for use. Finding our final hyperparameters, and final model initialization and training setup, and then we get to our training loop, custom training loop here. Right, when I run this, we can see it live, so you can see at the start. This is the prediction that it gives us, so you can see that the training losses. Yeah. Make it like that. So it's completely wrong at the start, and then we can already see that after 50 epochs, we're actually getting something that looks. Your training data set. I've got the data here, so it's sample data, but it's really not a big data set, and it's just to show, obviously in AI most of the time everyone says data is king, but this is also designed to show how little data you actually need to get something already up and running. And so this is it. So it's you can see on the left here it's PLI code, and then you have its equivalent Kotlin code here.
And at what granularity are you making the translation? Meaning, like, obviously you're not doing it like every program you speak something, right? Sometimes you have a big function, sometimes you have a big branches, so.
Are you translating like code file to code file, or function to function, or how does it work?
So I'll just show you actually running it afterwards, but here in my I've defined my actually running my model here, and I've done it file to file. So right now the input I'm giving it is a PLI file down here, and when I run that, I give it this entire file here. So let me get that bigger, and then we get its output. So way down there.
So then it's not generating token by token.
So you give it a whole file, it starts picking out tokens.
Yeah. Yeah. Okay, so in this notebook, I do everything. I use a custom transformer, and obviously I'm training it from scratch. Going forward, I think I want to reproduce this entire project, but actually fine-tuning already pre-trained models, which will be a lot simpler and will probably make the results even more efficient than they already are. But I already think this is quite cool. So that is it for me. If you have any more questions, I'd be happy to answer. Yes, please.
I think you could do this work also without using any machine learning.
Mm-hmm.
Just visiting the assessment tree of the source code and then translating, mapping that to the assessment tree of the private language, right?
Mm-hmm.
And is this work improving such process, the conventional transpiler? This might take one question, and second question: how do you check the quality of the outputs?
Could you repeat your first question for me?
The first is, I think using a conventional transpiler, I'm not expecting this, but you could visit the obsessive tree of a source code, and then you can map it to AST of the private language, right? So you can transform your code from one private language, right? That's the conventional way of doing it. I think that using the transformer. So my question then, this is an let's say, a way of improving that conventional method, or is something else, or how would you compare these two? Yeah.
Okay, so to answer your first question, obviously you can do this with a transpiler, but someone has to build this transpiler to be able to do all this. This could be a possible way of simplifying actually building the transpiler. I don't think it can completely replace the transpiler, but it can help someone that has to build a transpiler for a set of languages and make it a simpler task. And again, to check the errors and if it actually works correctly all the time. That's the main issue with transpilers. You still also have that issue anyway. And with this, you just have to, especially using AI, it can be very hard because it can always have hallucinations and invent or just be wrong sometimes. And so on this small example I showed you, it's correct, but over huge projects, we can't be sure right now using this method or that everything is correct anyway. No. Oh.
Expecting the PO1 is running on inference or something. When you're doing the translation to Kotlin, you're probably also doing like architecture changes, right? Is that part of the process? Is that going? Just maybe you can talk about it. But I'm just curious if that whole migration is being assisted by this and it's actually working out for you guys. Even if it's just theory.
Maybe we should talk about that.
Yeah, that's okay.
Yeah.
Well, our insight is based on
So right now, this isn't doing it. This is like a side project sort of I had where it's like an idea of something we could implement. But the idea is to adapt to architecture as well. Yeah. Yes.
But then thanks for mentioning hallucinations because so I see here like the spectrum on the one side is like what Anton mentioned with the concrete transpiler, which is I know what I expect, right? In the output, it's probably going to be as accurate as I have coded the transpiler. On the other end is probably going to be LLMs, right? It's very general purpose, just trained on some general purpose data, whatever. And then there I would expect a lot more hallucinations, right? Because it's not focused. Where would you place yours in the sense, because you have done some customization of the model, right? You've taken the Seq2Seq model, you changed the training data. My question is also, what else have you changed? Did you change the tokenizer or something like this? And two, would you think your doing something like this would reduce the hallucinations, or do you have some idea of it? You measure with more general purpose models.
So obviously, that's a great advantage of having your own custom transformer, is being able to adapt it perfectly to the task you want doing, and the tokenizer as well is adapted to my data and stuff. So this works very well. But could you repeat your second question?
Does it hallucinate less than a more general purpose model? Because you've done a lot of effort to customize your model.
Yeah.
Right, for your purpose. And the question is, if you have some measurements, or at least if you have some hunch on whether this fares better than the general purpose model in terms of hallucinations.
Yeah, so does it hallucinate less? Most of the time we say that the less data means less knowledge, and it means it can possibly hallucinate more. So considering on the amount of data I trained it on, it could possibly hallucinate more, but then again, it can't invent something it doesn't know. Considering it only knows how to translate the PL1 to the Kotlin, so it can't invent Java because it doesn't know Java. Whereas, like you say, there's a more wide-ranged model that has knowledge of other things, so it could possibly hallucinate and give a wrong answer. I can't give a definite answer to that. All we know is most of the time there are more possibility of hallucinations with less data. But then again, we've got models like CodeLlama that are specific on code, so they could possibly actually be better. The fine-tuning CodeLlama could give us better results than this. Yeah.
I think there's time for one last question.
Okay.
transpiler in traditional technologies, and they do not cover all possible inputs. Do you think you can combine that with your kind of solution? Maybe, if I have a compiler that covers maybe some PL1 statements, but not all of them, can I maybe use your AI solution to cover the parts that the transpiler cannot cover?
I think so. Yeah, I think the AI could understand looking at what you've already got with the compiler and possibly complete it. Yeah.
And then we can thank our speakers.